Hello dear students, I hope you are doing well. So today in this video we are going to do a numerical based on the formula which we discussed in the last video, the density formula. That is D is equal to mz by NaAQ, where A is edge length, Na is Avogadro's number, m is mass, that's molar mass, atomic mass, molecular mass, Z is the number of atoms, D is the density. So let us read the question and find out what are the variables given. So a metal crystallizes in face-centered cubic unit cell. It's face-centered. So we know if it is face-centered cubic unit cell, the number of atoms, that is Z, is equal to 4, which I mentioned in the last video. If it is simple, number of atoms is 1. If it is body, number of atoms is 2. If it is face, number of atoms is 4. Structure with cell edge length, that is A, is equal to 500 picometer. If density is 1.38, that is D is equal to 1.38 gram per centimeter cube. Calculate the molar mass of the unit cell. That means you have to calculate M. You know Na? Na is equal to 6.023 multiplied by 10 to the power 23 per mole. Now, the unit of length used here for edge length is picometer, whereas in density the unit of length, that is for volume, is centimeter cube. Now we cannot use two different units in the same question, so we have to convert the picometer in centimeter. So we know the relation 500. 1 picometer is equal to 10 to the power minus 12 meter, which is equal to 10 to the power minus 10 centimeter. So 1 picometer is equal to 10 to the power minus 10 centimeter. So 500 picometer is equal to 500 multiplied by 10 to the power minus 10 centimeter. So now let us use the formula. D is equal to mz by NaAQ. So from here, M will be equal to D, density, multiplied by Na multiplied by AQ by Z, that is number of atoms. Now density is given 1.38 gram per centimeter cube. Na 6.023 multiplied by 10 to the power 23 per mole. A is given 500 multiplied by 10 to the power minus 10 centimeter whole cube by Z is equal to 4. Centimeter cube and the centimeter cube here will be cancelled. So it's 1.38 multiplied by 6.023 multiplied by 500 cube. That means 500 multiplied by 500 multiplied by 500 multiplied by 10 to the power minus 10 multiplied by 3 minus 30 divided by 4. Now if you simplify this, you will get 24.7 gram per mole. So this is how we do numericals based on this density formula. There will be questions where you'll get the molar mass, you'll get edge length, you'll get number of atoms, you'll be asked to find density. So you can take more questions from the textbook and practice yourself. So the next topic from this chapter, which I'm going to study, is defect. Now what is defect? defect is something which is not perfect. There is, say we in a crystal, we arrange atoms. So if the arrangement of the atom is not perfect, that means something is missing or something is added extra, that is defect. So there are two types of defect, that is point defect and line defect. Line defect is not in the syllabus, so we'll study only point defect. Now, point defect are further classified in the stoichiometric point defect, non-stoichiometric point defect, and impurity defect. Stoichiometric defect, they are further classified into two types, Scotchy defect and Frankel defect. Non-stoichiometric, they are classified into two types again, that is metal excess defect and metal deficiency defect. Now, first, what is the difference between stoichiometric defect and non-stoichiometric defect? Now, say you have a crystal. The atoms or the ions or the particles, you can say, are arranged in an orderly manner. Now, the defect will arise when there is an additional atom, or the atom is missing from the crystal, or atoms are missing from the crystal. Now, if the defect causes no change in the formula, that means even if there is a defect, but the formula will remain same, is known as stoichiometric defect. Like say you take a sodium chloride crystal. Now in a sodium chloride crystal, there will be many sodium ion and chloride ion. Now if equal number of sodium and chloride are missing, the formula will remain same, that is NaCl. This defect is known as stoichiometric defect. But say if you have FeO, ferrous oxide, and due to deficiency or due to defect, it forms Fe 0.950. Now you can see the ratio of ferrous and oxygen, it changes. That means the formula changes. So this is non-stoichiometric defect. So let us study this in details. We start with Scotchy defect. Now in case of Scotchy defect, let us take the example of sodium chloride, that is Na positive, Cl negative. So this is a crystal formed by arrangement of sodium and chloride ion. So this is a crystal. There will be more ions here. Now, in case of stoichiometric defect, equal number of positive and negative ions are missing from the crystal. If there is one positive ion missing, there will be one negative ion missing. Now, this will create a void in the crystal. So this defect is known as Scotchy defect. So the defect which arises due to equal number of positive and negative ion missing from the crystal. Now this is seen in the case of ionic compounds where the cation and the anion they are of similar sizes, like AgCl, AgBr, NaCl, etc. Now, what about the effect of this defect on the density? The density formula is density is equal to mass by volume. Now, the volume remains same. Now, since the ions are missing from its position, is missing from the crystal, the overall mass will get reduced. That means it will decrease. So, since the mass decreases, density also decreases. So, for Schottky defect, density decreases. Next, let us see Frankel defect. In Frankel defect, so this is the arrangement of ions, that is positive ion and negative ion. We'll take the example of sodium chloride again. So Na positive, Cl negative, Na positive. Now say this is a crystal. Now in case of Frankel defect, an ion, say positive ion, is missing from its position, but it's not missing from the crystal. Now in case of Schottky defect, the ions are missing from the crystal. But here in Frankel defect, the ions will be missing from its position in the crystal, but not from the crystal. That means it will occupy some random position in the crystal, which is known as interstitial position. Now, because of this interstitial position in the crystal, it creates a defect. This defect is known as Frankel defect. Now, the effect of Frankel defect on density. Now, density is equal to mass by volume. Volume is same. Now, mass. Now, here the ions is missing from its position, but it's not missing from the crystal. So the mass of the crystal will not change. Now, if the mass of the crystal does not change, the density also remains the same. So for Frankel defect, the density will not change. There will be no change in density. Next, for non-stoichiometric defect, we have metal excess defect and metal deficiency defect. So first let us see metal excess defect. So from the name itself, you can make out metal excess. That means the metal will be in excess. If you take a solid, an ionic solid, the cation number will be more than the anion. Whereas in case of metal deficiency defect, the number of cation will be less than the number of anion. Now, this metal excess defect can be because of two different possibilities. First possibility is the cation is missing from the crystal. So you have this cation, anion, cation, anion, cation, cation, anion. So say this is a crystal which is formed from ionic, that is from ions. Now, in case if the anion is missing from the crystal, so if the anion is missing from the crystal, it will go out and there will be electron trapped here. Now, how this electron will be trapped? Say sodium, if it comes and takes chloride, Now sodium ion will take the chloride ion. So that means the sodium metal will give out one electron to form sodium ion. Now this electron is trapped here in the anionic vacancy. That means the vacancy created by the anion. Now if you look at this, you'll find the number of cation here is more than the number of anion. So this will cause metal excess defect. Now the second possibility, the crystal they have equal number of positive and negative ion. Now in case if there is an additional positive ion in the crystal, like an impurity, so if there is an additional positive ion in the crystal, now the number of cation again becomes more than the number of anion. So this also will cause metal excess defect. In case of metal deficiency defect, so the name itself speaks about the type of defect, metal deficiency defect. That means the metal will be deficient. So say you have this crystal. Now let us take the example of Na, or let us take A positive, B negative. A positive, B negative. B negative, A positive, B negative, A positive, B negative. Now from here, say two cations are missing, and one of the cationic vacancy is occupied by another element or cation with charge say 2 positive, let it be X 2 positive. Now the charge is balanced because 2 A positive missing means 2 positive is missing, but there is an impurity, or you can say an external ion having charge 2 positive. So the overall charge will remain same, but there is a vacancy, and the vacancy is because of the missing cation. So this type of defect is known as metal deficiency defect. Now in this crystal, you can see there is a foreign ion which is not part of the crystal. The crystal is formed of A positive, B negative, but X2 positive will act as an impurity. So this is also considered as impurity defect. So this is what we have in the solid state chapter. We start with solid, then we study the classification of solid. After that we study different types of crystalline solid. Then we have to study unit cell, crystal lattice, different types of crystal lattice, different types of unit cell. We have to calculate packing efficiency. We have to study packing in crystal. We have to study defect. So please go through the videos. Try to understand. If you have any doubt, you can call me or you can text me anytime you want as per your convenience. Please go through the video and study well. Thank you.